Hello, and welcome back to the course on classical electromagnetism. So we are now on the 6th chapter for this course, which will now talk about electrodynamics. We will now consider moving charges and what is its effect on its electric field and magnetic field. So before we proceed with this, the first lesson, let's first discuss some, review some concepts. So in the previous lessons, we have discussed about Gauss' law, wherein it's just the closed integral of E dot dA, which is just the total electric flux on this surface, dA, we call the Gaussian surface, and it's just equal to the charge enclosed over epsilon naught. We also discussed about the concept of current, which is just the change in charge per unit time, dq dt. And if you're given the surface current density K, you can get the current by getting the integral of K dot dl. And if you're given the volume current density J, then you can get it. You can get the current by integrating J dot dA. So, by the way, this is a surface integral. These are surface integrals. Okay. So, for our first lesson, we will discuss, maybe in depth, because you have already discussed this in your basic electromagnetism. So, we will discuss one of the more familiar and famous laws in electrodynamics called Ohm's law. So when you have a material and current flows through that material, say with current density J, the reason why charges flow through that material is because there is a non-electrostatic field or an electrodynamic field. So this electrodynamic field is actually the one pushing or pulling the charges, causing them to flow. Now the relationship between the current density and the electric field is given by Ohm's law. So this is Ohm's law. J is related to E by this proportionality constant called sigma. And sigma here is not the charge density, but sigma will now be designated as the conductivity. So sorry for the repetitive use of variables. So sigma is the conductivity. This is the measure of how much a material can conduct the flow of charges or conduct current. So the conductivity is inversely proportional to the resistivity. So the resistivity is the opposite of conductivity. It resists current flow. Yeah. So if conductivity lets current flow, resistivity resists the flow of current. So if you have a steady state current, the electrodynamic field is actually non-diverging, meaning its current density is also non-diverging. So it has a uniform direction. If current is flowing in a material, and since every material has a resistivity, then there will be some degree of resistance of how the charges flow through the material. And when a material resists the current flow, some of the energy of the current will be converted into heat. So the work done by the electric field, which propels the charges or the current to flow, is actually some of it is actually converted into heat, and they are given by this Joule heating law. So it actually describes the power. So V times I, V is the voltage or the potential difference maintained at the ends of this conductor. I is the current flowing in this conductor. Or it can also be given as I squared R, where R is what we call the resistance of your material. So take note, you already have discussed about resistivity versus resistance in your basic electromagnetism, so you should recall that one. So meaning energy is always dissipated in a material with resistance or with resistivity. So energy is always lost in a material with resistivity or resistance. So let's have an example. So suppose we have a cylindrical resistor. It has a length L. So it has a length L and resistivity rho, and is maintained at a potential of V at both ends. So one end is a positive potential, the other end is a negative potential. So you are asked to find the magnitude of the current flowing through this cylindrical resistor. Okay. So we start with Ohm's law. Let's just use the magnitude version. So J is actually sigma over E, where sigma is 1 over rho. Rho here is the resistivity. It's not the volume charge density, but here rho is the resistivity of the material. Okay. So let's just use the non-vector form. Okay. So since I is J dot dA, and in this case we will assume steady state current, so meaning J has no divergence and J is actually uniform. We can take it out of the integral, and then you're left with integral of dA, which is the total area, and you will just get J times A. So therefore current is J, which is E over rho times A. In this case, if you will recall, the potential difference is integral of E dot dL, and for steady state current, this electric field is actually non-divergent, so it's uniform at all points, at all similar points with respect to this dl, the differential length L. So basically this is just E times L. So the magnitude of the electric field therefore is just V over L. So E here is V over L. So you will have V A rho L. Okay. I can actually rewrite this as V over rho L over A, where this term rho L over A is actually the definition of resistance R. So we then get I is equal to V over R, and this is maybe the Ohm's law that you are familiar with. V is equal to IR, or I is equal to V over R. So there's a linear relationship between voltage and current, and if this is the case, if the relationship between the voltage applied to a material and the current flowing through a material is linear, then that material obey Ohm's law, and usually we call that material as an ohmic material. So in this case, R is rho L over A. Take note here the difference between resistivity and R. So resistivity is similar with any constants of a material. It just depends on the type of material. But resistance depends on three things: the type of the material, which is given by the resistivity, the length of the material, and the cross-sectional area of the material. So A here is the cross-sectional area. So let's have another example. So suppose we have a conducting cylindrical shell. So you have two conducting cylindrical shell with inner radius A and outer radius B. The inner surface is maintained at a positive potential, and the outer surface is maintained at a negative potential, and the potential difference is V. So we are asked to find the current and resistance of this conductor. So if you will notice, since this is the positive surface here, the inner surface, and the outer surface is the negative surface. So the electric field is actually outward, meaning the current will also be outward, and the current density is also outward, radially outward. Okay. So we already know the field of a line charge, so we can actually assume that our inner surface is basically a line charge with line charge density lambda. So in that case, we already know actually the answer. So the electric field of a line charge is actually lambda over 2 pi epsilon naught s, and the direction is s hat, just as we predicted. So the electric field is radially outward, is lambda over 2 pi epsilon naught s s hat, where s is the radial distance. Okay, so to solve for the current, it's just the volume charge density, sorry, volume current density dot dA. And since from Ohm's law, J is just sigma E, so we'll get sigma E dot dA. And this is basically Gauss law, the integral of E dot dA. And this is just equal to the charge enclosed over epsilon naught. So you will get sigma. The charge enclosed is actually, for a line charge, is lambda times L over epsilon naught. So this is Gauss law. It's equal to charge enclosed over epsilon naught. The charge enclosed is lambda times L. Charge per unit length times length, you get charge. Okay. So this is our current. But it's not yet the final form. So from our the voltage between points A and B is actually from B to A of E dot dL. So we already know the electric field. In this case, our dL is ds, since our electric field is along the S. So this is actually ds s hat. So this will give us from B to A, the electric field is lambda over 2 pi epsilon naught s hat, with that with dl, which is ds s hat. So you have s hat at s hat equal to 1. So basically, you will have an integral of ds over s, and the answer of that is ln. So lambda is a constant, 2 pi epsilon naught is a constant. You can take that out of the integral, and you will be left with integral of ds over s evaluated from B to A. And this will give you a value of lambda over 2 pi epsilon naught ln of B over A. Sorry, there's just a negative sign here. Sorry. So there's a negative sign, but you can get rid of the negative sign if you invert the limit. So from A to B. So it's just actually the same. So negative integral from B to A, from negative to positive, or you can integrate from A to B, from the positive to the negative potential. Okay. So this is our V now. So we can actually rewrite this, since we know that I is given by sigma lambda L over epsilon. So I can actually rewrite this as something like this. Lambda sigma L over epsilon naught 1 over 2 pi sigma L ln of B over A, where this one is now my current, and basically this one is my resistance. So this is actually my current, And this is actually the resistance of this conducting cylindrical shell. This is the current and this is the resistance. By virtue of Ohm's law, V is equal to I times R. Because we already solved for I. Okay. You can also, instead of sigma, the conductivity, you can actually write this. So it's just the inverse. The inverse of sigma is rho, the conductivity, and the inverse of the conductivity is rho, which is resistivity. So you can also write this as rho ln B over A over 2 pi. Yeah. So that one. So this is our result. Okay. So let's have another example. So this is a discharging capacitor. So find the current again, but this time the current is actually time dependent. It depends on time, because if you have a fully charged capacitor, this is an RC circuit, or RL circuit rather, or sorry, RC circuit, resistor capacitor circuit. That is, the capacitor will actually give all of its energy instantly to the resistor. So you are asked to find the time independent current and the total energy delivered or supplied to the resistor. Okay, so first things first, we know that the capacitance of a capacitor is Q over V, and by virtue of Ohm's law, V is equal to I times R. So therefore I can get Q is equal to I R C. In this case, our current is negative dq dt. Negative because the current in this circuit is decreasing, because originally there will be a surge of current, but that current will keep on decreasing and decreasing until it will become zero when all of the energy of the capacitor is delivered to the resistor. So the current is actually decreasing. So when the current becomes zero, that's the time that there's no more energy left in the capacitor and it's already being dissipated or lost or delivered to the resistor. So you will have Q is equal to negative RC and dq dt. So solve for Q. So we have, so we'll get dq over Q is equal to negative 1 over RC dt. You integrate this one from time is equal to 0 to a final time t, and say from an initial charge Q naught to a final charge Q. So the integral of this is ln of Q. So this will become ln of Q over Q naught is equal to negative t over RC. Solve for Q. We take the exponential both sides, so e to the ln is just Q over Q naught, and you will get Q as a function of t is equal to Q naught e to the negative t over RC. That one. So you just take the derivative of that, because this is our definition for current, negative dq dt, negative derivative of this with respect to time, and you will get so I is equal to negative derivative of this with respect to time, so you will get Q naught derivative of e to the u is e to the u du, so e to the negative t over RC times negative 1 over RC. Okay. So you will get negative or positive now. It's positive Q naught over RC over e to the negative T over RC. But take note, the capacitance doesn't change before and after the capacitor is loses its charge. So it's actually equal to Q naught over V naught. So capacitance is charge per unit voltage, Q naught over V naught. So therefore, Q naught is just equal to C V naught. So this is actually C V naught. So C will cancel out and you will get V naught over R, e to the negative T over RC. And V naught over R, so the initial voltage will actually result in an initial current. So I naught R, meaning I naught is V naught over R. So this is just the time dependent current will be equal to the initial current, which is just V naught over R by virtue of Ohm's law, e to the negative T over RC. So this is the time dependent current. It actually decays exponentially. So that's a very fast decay. It's an exponential decay. So this is the exponential decay in the current. So you will notice as time approaches infinity, that will actually approach to 1 over e to the negative infinity or 0. So at infinity, at time is equal to infinity, the current will decrease to 0. But the initial current at time is equal to 0. So you have e to the 0 or 1. The initial current is V naught over R, or that's our I naught, initial current. Okay. How about the total energy delivered or supplied to the resistor? So take note, when the capacitor is fully charged, the energy stored in the capacitor is, say, U naught, which is 1/2 C V naught squared. Since the initial voltage of the capacitor is V naught, then the initial energy, electric potential energy stored in the capacitor is 1/2 C V naught squared. But of course, the final potential energy of the capacitor is 0, because all of this energy is actually delivered to the resistor. So actually, this is also the answer to this. Find the total energy delivered or supplied to the resistor. But you can verify that by using the concept of power. So power is work per unit time, or differential work over differential time. Therefore, the differential work is just P dt. You integrate this to solve for the total work, or the total, and which is just the total energy, or the total work done on the resistor, or the total work or energy delivered or supplied to the resistor. And we have P dt. So P is I squared R dt. So we already have the current, this one. You square that one. So you take R out of the integral. So you have R. And then it's from 0 to t, no? It's from all values of time, 0 to infinity. 0 to infinity. And you have I squared is V naught squared over R squared. So you will just get V naught squared over R. And then you will have e to the negative 2t over RC, the square of e to the negative t over RC dt. So this is just a simple integral, e to the u du. And basically, you will get 1/2, this term, 1/2 C V naught squared. So meaning, all of the energy of the capacitor, the initial energy of the capacitor, is just delivered to the resistor, 1/2 C V naught squared, as it should be. Okay. So when all of the energy of the capacitor is delivered to the resistor, then that's the time that there will be no current flow, because the capacitor is now fully discharged. Okay. So let's have the reverse. The reverse is a charging capacitor. So find the time-dependent current of current flowing. Sorry, wrong grammar. So current flowing through a battery, resistor, and capacitor in series. So you have a battery, a resistor, and capacitor in series. So the current is also time dependent. So also find the total energy supplied with the battery and the total energy delivered to the resistor until the capacitor is fully charged. Okay. Take note that current only flows when there is a difference in potential. So originally, the capacitor has zero potential. Because it has zero charge, it has zero potential. But as time goes on, the current supplied by the battery is actually decreasing, because some of that current, some of that energy is actually delivered to the resistor and is used to charge the capacitor. So meaning there will come, the current here, similar in the previous problem, the current is actually decreasing in this case. So it's decreasing, and it will decrease, the current will become zero when the capacitor becomes fully charged, meaning the potential of the capacitor and the, is now equal to the potential of the source, V0. So there's no potential difference, there's no more current flowing, because there's no difference in potential. Okay. Sorry, when I say there's no potential difference, it's the combined potential difference of the resistor and the capacitor. So, correction. Okay. Okay. So the voltage of the source, in this case, the voltage of the source will be divided, because this is a series connection, the voltage of the source will be divided into the resistor and the voltage of the capacitor. So this V0 will be divided into the voltage of the resistor and the voltage of the capacitor, because this is a series connection. A series connection is a voltage divided. So the voltage in the resistor is IR by virtue of Ohm's law. The voltage in the capacitor is Q over C. So this is V0. Again, I here so I here is dq dt. This is actually I would like to make a correction. dq dt is the charge in the capacitor. So in the discharging case, dq dt is negative because the charge in the capacitor is decreasing. But here, this is charging a capacitor. So the charge in the capacitor is actually increasing. That is why I is a positive dq dt in this case. In the previous case, I is negative dq dt because the charge in the capacitor was decreasing, because it's giving it to the resistor. But here, the supply, the voltage supply, the battery is actually giving charge to the capacitor, so it's increasing in this case. So this is dq dt. So we can actually solve for I here. If we solve for I, then we will get VO minus Q over C over R, and this is equal to dq dt. So this is still simplifying. We have V0 over R minus Q over RC. And then solving for dq, we get dq so we can simplify this as 1, say negative 1 over RC. We take negative 1 over RC out, and you will have Q minus CV not. And then we change variable. Change variable from Q to Q prime. So we let Q prime be equal to Q minus CV not. So therefore dq prime is equal to dq. So in that case, we can have dq prime dt is just equal to negative q prime over rc. So we can now solve for dq prime over q prime is just equal to negative 1 over rc dt. Integrate it, you integrate this one from 0 to t. But now q prime, the value of q prime at time is equal to 0 is when q is equal to 0. So that will give you negative cv naught. So the lower limit here is negative cv naught, and the upper limit is q minus cv naught. That one. So you can now solve for q. So you can have, this is ln of q prime. So ln of q minus cv naught over negative cv naught is equal to negative 1 over rc dt. And then solve for q, you will actually get a similar result with the previous problem, or not quite similar. So you will get q as a function of t is equal to cv naught minus cv naught e to the negative t over rc, or cv naught 1 minus e to the negative t over rc. So it's actually quite different, the charge. But if you get the current, if you solve for the current I, which is just dq dt, you will still get the same result. So you will still get the same result. So the result that you will get is this one. So the current in the circuit, flowing in the circuit, is still decaying exponentially, because that's actually, this battery is actually charging this capacitor. But dq dt, the change in charge in the capacitor with respect to time, is actually increasing because this is charging the capacitor. So if you find the total energy, so you do the same for the total energy. You will actually use the same formula as we did before. So work is just power times time, which is I squared R times dt. This is for the work energy delivered to the resistor. For the energy of the source, it's just the power of the source is just V naught times I dt. So this will give you 1/2 cv naught squared. This will give you cv naught squared. So this is the power supplied by the source. It's cv naught squared. Half of that goes to the resistor, 1/2 cv naught squared, and the other half, the other 1/2 cv naught squared, goes to the capacitor. So that one, the total current supplied, or the total energy supplied by the battery, is cv naught squared. Half of that goes to the resistor, and half of that goes to the capacitor. That one. So when the capacitor is fully charged, there's no more current flowing in the circuit. Okay. So again, the work, or the energy delivered to the resistor, is 1/2 cv naught squared, and that is the same energy, the total energy stored in the capacitor, 1/2 cv naught squared. So that is it for this lesson, and for the next lesson we will be discussing about EMF. So I will see you again in the next lesson.